So an interesting thing happens with our compound interest formula. The more often something is compounded, the more money you're going to make over time. So we saw that compounding once per year, it's better if it's compounded monthly, because then you can make interest on the interest you've already made. So if theoretically we kept on compounding something more and more and more, we went from monthly to weekly. We went from weekly to every day. We went from every day to every hour. Every hour they gave you a little bit of extra money in your bank account. Then you went from every hour to every minute to every second to every millisecond. And eventually you would get to the idea that it could be compounded continuously all the time. And when it's compounded continuously, in other words, when n is a super big number, or as n goes to infinity, this formula changes to this formula. It still has a, which is your amount, p, which is your principal or your starting amount, but the number e appears. Your interest rate is still in there, and it's still as a decimal, and t is your time. You no longer have n because the compounding periods are infinite. It's continuous. And this formula is the formula that is used to model anything that has continuous growth. Whether that is an interest rate, although no banks will pay you interest continuously, nor will any bank charge you interest continuously. Because if you found out they were charging you interest all the time, every second, and making money on your money every second, you probably would go with a different bank. Even though the results are not as bad as you think. So we're going to look at this. We're actually going to switch A and B. We're going to do B first and then A. How much money would you earn, $2,000, invested 5.5% for 10 years if it was compounded quarterly? So we're going to do that one first. And then we're going to look at the other formula and see what happens if it was compounded continuously. So starting off with quarterly, how much did we have? $1,000? $2,000. Oh, look at this. Good recovery. 1 plus interest rate was 5.5%. Compounded quarterly is only 4 times per year. And this is after 10 years, so it'll be 4 times 10. This we can just put our numbers in directly. 1 plus 0.055 divided by 4 to the power of 40. So compounded quarterly means that 4 times a year, in other words, every 3 months, they would pay you your interest. Now 5.5% interest on $2,000 is $110. So they would divide that 110 by 4, and after the first 3 months, you would get about $28 or something. And then the next month, you would make interest on the whole amount, or the next 3 months, you would make interest on that $28 and the other one. Now, here, interest is compounded continuously. So as soon as you put the money in, new money starts coming in from your interest. Not a lot at a time, because they have to figure out, well, they're still thinking there would be $110 in a year, and in 1 second, you would be privileged to 110 divided by 365 divided by 24 divided by 60. Very tiny amount. But you would get something. And then you would make interest on that something. So if compounded quarterly makes $3,453, what do you expect this one to be? Okay. So here we go. There's our formula for continuous growth. Again, we have $2,000 initially, and interest rate is 0.055, 10 years. We plug this into our calculator and prepare ourselves for disappointment. Wow! Look how much more money you get in 10 years. It's like $13. In 10 years, you won't even be able to buy a Big Mac for $13. They'll be like $28 a Big Mac at McDonald's. But you will have made that $13 more. So the interesting thing, compounding is important. And compounding does make a difference over time. But the biggest thing that's going to make your difference in any kind of interest thing that you ever encounter in your life is the interest rate. A small increase in the interest rate, which here is 5.5%, can make a huge difference in amounts. And that's something I'm going to show you next class with mortgages. And it's fascinating. But yeah, even if we retype this amount that we had before with the compounded quarterly, and I instead change it to 6% instead of 5%, so only a half percentage, that already increases it by $170 with a 0.5% more interest rate. So when interest rates go up or down a little bit, it can make a huge difference. Well, that depends, and it depends on your timing. But when we look at mortgages tomorrow, or tomorrow we have a quiz, but after, maybe on Wednesday, when we look at that, we're going to find out that right now you can get mortgage rates around 3.5%. So the bank is charging you 3.5% interest, which is relatively low. You can find some that are even lower, sometimes lower than that, like 3%. Ask your parents, ask your grandparents before Wednesday, what is the highest interest rates that they can remember banks charging on loans? Because there are some crazy numbers, and I need those numbers from you by Wednesday. So you got to go home, you got to ask, what are the highest interest rates you remember the banks ever charging you? Because they'll know, they'll remember. Ask your grandparents, ask your parents, because there's a huge swing in those numbers, and there's some very surprising results. But at 3%, like 3% means that if you buy a house now, and if they just compounded it annually, normal houses right now are somewhere in Winnipeg between $300,000 and $400,000. That's sort of average house price. 3% on $300,000 is a lot, right? That's like $9,000 a year in interest. So you're trying to pay off your house, and if you just pay $9,000, you will just pay the interest and you won't pay any of your house off that year. And when you pay for your house, let's say you can afford $12,000 a year to pay for your house, in your first year you'll only pay off $3,000 of your house. The rest of it just paid off interest. And so you end up paying a lot of interest over time for your house. And we'll look at examples like that. Terribly fascinating. But for today, we're starting with continuously compounded. Now, in real life, there's no bank that charges you interest continuously, because if you found out that, because there's a perception that this would be a lot more, right? You expected this number not to be just $12 more, especially in 10 years. So no banks are going to do that because it would just be bad PR and they're not going to get any customers if they charged interest continuously. But we do use this formula quite a bit when we're looking at population. So some of the examples we're going to do later with this is going to be with population. So here, let's do a couple more investment ones. These questions, you will know that you need to use the PERT formula, as I like to call it, anytime the question says that something is continuous. So here, investment of $200 is compounded continuously. In 3 years, the investment is worth $235. What is the interest rate? So when we put everything that we know into this formula, we don't know the rate. And now we're solving for R in the exponent. When you solve for something in an exponent, how do you do that? You use logs. Now, since the base is e, we're going to use natural logs. Now, logs and natural logs is exactly the same work. You could choose here, and in fact, we didn't do this on our example this morning, but I always like to divide first if we can. With the question with the 500 and the 200, we didn't. Then you have to use your log law that adds, and that's not wrong. But if you divide first, it makes it a little bit shorter to write. Now we can take the natural log of both sides. I'm not even going to reduce that fraction. And does it make sense that that exponent could now come out in front? One of the reasons we chose the natural log is what is the natural log of e? E to what power is e? 1. And so if that's 1, then if I want to solve for r, all I need to divide by is 3. And we find out that the rate was 0.0, should use approximation signs, 538. Rounded to 3 significant figures, or 5.38%. I'm going to leave this one for homework, and we'll probably get some time at the end of class to work on that. And now we are going to look at continuous growth when it is more often used, and that is in population. Since the human population is large, it's large enough to be modeled by a continuous growth. That our population is always growing. There's always people being born. There's always people that are dying. But overall, we are growing. And since our numbers are large enough, it can be modeled well with a continuous growth model. So here we're looking at the population of Vancouver. 1981, 1.38 million. And if the population has been growing continuously in Vancouver at a rate of 1.7%, we could say, what is the population going to be in 2011? So again, the fact that it has continuously means that we're going to look at a PERT formula. We want to find the amount, the original amount in 1981, 1.38 million. The rate as a decimal, 0.017. And what am I going to plug in for my time here? 30, because from 1981 to 2011 is 30 years. Nothing complicated to solve here. We can just plug everything in exactly as we see it. And it says to the nearest tenth of a million. So I got 2,298,000. Uh-oh, did I type in something wrong? Okay. Whew. So that'll be 2.3 million if you round it to the nearest tenth of a million. When will the population reach 6 million? So again, we've got our formula. Now we're going to be trying to solve for t, for time. Are you okay if I start with that instead of writing all the zeros?
Sure.
Yeah? So I'm instead of writing 1,380,000, I just do 1.38 and 6. And then I've got E, the rate is still 0.017. And we want to find T. So again, I'm going to divide both sides by the 1.38 first. Just to get my power all by itself. How do I solve for something in an exponent? I'll log both sides. And since the base is e, I'm going to take the natural log of both sides. Does it make sense that that exponent would come out in front? And natural log of e is equal to 1. So when we type this in, you get 86.5 years. What does that mean? In the year 2067 and a half. So sometime in the year 2067, the population should reach 6 million. Are these accurate? When I made the question, I think I made up the numbers. When the population of a herd of gophers was first studied, it was 15,000. 6 years later, it was 18,000. If it continues to grow continuously, how long would it take to triple? Yes?
What is Winnipeg doing now? Didn't that ground
Yeah, that's why it's not turned to winter. everything's messed up. Now they're extinct. Anyways. So in this one, it's continuous. So we've got this formula for continuous growth. We want to find out how long. The question says how long, so you know that you want to solve for t. So the question is, do we know A, do we know P, do we know R? We don't know R. We've got a problem. We're told that it grows continuously, but we don't know R. Before we can solve for t, we are going to have to find R first. So the question is, do we have enough information to put things into that formula so the only thing we don't know is R? Because we got 6 years, we've got an initial amount of 15,000. It becomes 18,000 in 6 years. So in this question has 2 steps because we first have to find R. Once we've found R, we're going to be able to use that to find t. Now again, I'm going to divide both sides by 15,000. Are you okay if I just write 18 over 15 because all the zeros would go away? We're solving for something in the exponent. We do that by taking the log of both sides. And since it's a base of e, we're going to take the natural log of both sides. That exponent could come out in front. The natural log of e is 1. So r is going to be the natural log of 18 over 15, all divided by 6. Now on our calculator, if we type this in, get our fraction, natural log 18 divided by 15. All divided by 6. We get a rate of 3%, or r is 0.03. Now the hard part about these questions is you are going to want to round this. But since this isn't our final answer, I'm going to just put dot, dot, dot there to say I am remembering all of those decimal places. In fact, I'm going to go to my calculator and I'm going to store it. And I'm not going to store it as x, I'm going to store it as r. Because that's my r was here, so that'll help me remember. Now that we found r, we can go back to our formula and say, if the population grows continuously, how long is it going to triple? Now we can find t. What numbers do I use? Okay, you could use 3 and 1, and it will simplify to that. But one of the things that people get confused on is they're like, should I use the 15,000 or should I use the 18,000? Does it make a difference? Well, if you use the 15, what number do you have to put here? 4,500. If you use the 18, then you'd have to put 54,000. But either one, when you divide both sides, you are going to get 3 equals. And you see how I'm, because we're tripling, it's going to be 3. Yeah. You could go, it would be fine if you went 3 equals, because you know how that tripling works, and doubling would be 2 equals. That would be fine. Now we're going to take the natural log of both sides. And again, this exponent could come in front. Natural log of e is 1. So I can go to my calculator. I can write natural log of 3 in the top of my fraction divided by, and I can steal r from before and get 36.15 years. You got 36.6. Did you use your stored value, or did you put 0.03 in? So if you round it, it makes a big difference. And the final exam has an error for rounding early. So you need to keep all of your decimal places all the way along and only round for your final answer. So here we get 36.15, and we should include the units as well. Years. Okay, so what we are going to do right now, there was the one question that I left from earlier. You are going to do that one, and then you're going to do the last question as well.